Hello everyone, welcome back to Algorithm and Data Structures course. And this semester we are going to talk about the following topics: games,
Well,
strings algorithm. Okay, what? Uh, okay, games, strings algorithms, computational geometry, and you can suggest any topics you want. Um, mm, I think we have a time um, to take it apart. So today we are going to talk about combinatorial games. You can look in detail on the following resource this topic. Um, okay, what is combinatorial game? Okay, um, what is combinatorial game? Um, that's a player game where we have two players, only two players that moves uh, turn by turn. And in combinatorial games, we have all information and all possible moves are determined. Uh, you have you can um, I can give you an example like these games. Okay, consider the first problem, a game of matchsticks. There are n matches, and we can take, and each player can take one to the two and so on k matches. The first variant of this problem, the one who can't make a turn a match loses. Um, okay, we can apply dynamic programming or recursion strategy to solve this task, and who can solve it by this approach? What will be the base of our step of our dynamic programming in this case?
false would be like nothing taken.
Okay, nothing taken. Now matches. If we have now matches, that's hence the first player will lose. We denote losers like P and wins like N. So next, it's obvious that next will be N. Then it will be what? It will be P and so on and so on. Okay, why is it true? We in this case, whatever we take our сколько бы вы ни взяли our matches, we get that all moves happens to n in in negative situations, in positive situations, by the way. And in this example, n means next, next who will turn wins, and p means previous who take a turn wins. Okay, second variant of this problem, whoever takes the last one loses. Okay, how look like our DP? How looks like our DP? Okay, whoever takes the last one loses. So what? Okay, it will be a negative situation, it will be positive, and so on. Negative, 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 and so on, and negative, uh, negative 2, k plus 1, and so on positive. Okay, that's very simple, I think. Uh, Next, consider symmetric strategy. Uh, we will win, in this case, we will win for O1, and consider the following problem, round table. Two players take turn, place identical points on the table, on the round table, and the one who cannot make a move loses. Okay, and who will win in this situation? The first player or the second player? It's not obvious, I think, for all.
It depends on the number of coins. If the coin is
No, no,
even,
no, no,
then
no. It's not the. It does not depend on that. Try to apply symmetric strategy, but but как бы okay. The first one, the first player who take turn, uh, take put our coin to the central of our round table. And what happen? What happens next? We apply symmetric strategy. Um, Strange. What happens next? Okay. Next, second player put coin whatever he won, and our turn will be like reflect their reflect his turn, and that's it. And it's obvious that in the in um, as we know that yes, we know that we the last step will be looks like we fill our table with coins, and we put we put the second player put some coin, and we reflect their coin, and we win. We will win. The first player will win. Okay. The trick is place first coin on the central of the table. Okay, I think it's clear. The next problem, we consider we consider table, and we have policeman, a bandit. Policeman can move diagonally, and diagonally, up, down, right, and left, and bandit can move only up, down, right, and left. So the first question: who will win if the policeman the policeman move is the first player?
So the policeman will win.
Policeman will win. Okay, but if he located in this point, for example, it, policeman will lose, and depends on and this and win and win depends who will the first whale player and the and depends on positions of players. Okay, no, we can we can launch, for example, the extra or a star algorithm and сравнить, сейчас сравнить, compare our minimum lenses to uh, um, compare, нет, сейчас, what we will do. Okay. We compare to our lenses. If the bandit, for example, exit from here, we compare this. Сейчас we compare what the lens of this and this, and who will the first wins. I think I think it's clear to see. My explanation it's not good because I can't explain it in English well, I think. But I think you understand me. Okay. Do you have questions about it? I can explain, but you can just ask me questions and I explain you what I mean. Okay. Next problem. We have two identical piles of stones. Two identical piles of stones, and the player can take any number of stones from first or second pile, and who will lose, the first player or the second player in this case?
The first player,
Why?
because he will start first, his like he will not be able to make a move first.
What what the second player must to do to win in this situation? Must do in this situation? How how the second player and reply on steps, on first player steps? Look at the topic. Okay, if the first player take
Player just take all of these stones.
I didn't hear you once again.
Is it possible for the
For the
to
what?
take all of the stones?
Yes, yes, it's possible.
Stone.
Yes, yes, it's possible to take all the stones of some piles of any from any pile. You can take any number of stones, but only from one pile. And notice that we have equal count of stones. Okay, the first player will lose. Why? Because if the first player take k piles, k stones, the second player have to take k piles from second pile from second pile too, and and so on, and we get that first player take the last stone from some pile, and the second player replies uh, in the same way, and the first player will lose because he cannot make any moves. Okay. Okay. Do you have any questions? I think it's clear. I think it's easy. Okay. We consider a little bit later nim game in the next lecture. But look at description of it. There are several piles of stones. It's generalization of previous problem, and we can make moves we can do it like in this problem, and and that's it. And we consider a little bit later how to solve this task. It's it will be the theorem in the next lecture. But but имейте в виду. Okay, the next is Wilfos game. We have two piles of stones, m and n. M and n is not equal in this case, and it's allowed to take any numbers of stones from piles, or take equal number of from both. For example, if we locate it at this point, we can make moves like this, or like this. Okay, and we will solve this task using DP, using dynamic programming. The base of DP will be we just this will be this scale will be loose, and this will be wins. And notice that if we just we iterate through all this array in in trivial order, we start from this and look and move like this and so on, and notice that if we cannot move in this for example cal, if we cannot move to positive to p mark, it means we loses because n is winning mark. In this case we just can make move like this, and we will win. Okay, and our table feel like this if we do the same thing. We just check that we in any if any cal that reachable from our is n, that means we have to we lose. The first player will lose. And if we have if there exists some move to some point that marked as p, we will win, and so on. Do you have questions? Okay, you have not. Okay. Next is Hackenbush. Given a graph, an undirected graph, and we can cut any edge from this graph, and vertices that not reachable from S will be removed, and edges will be removed. Okay, we can imagine our graph like this or like this. It's two identical graph, but this representation will is better. Okay, and notice that nim game that we considered, nim game, not this game, is equal, сейчас эквивалентно, забыл, equally to, if we have stones, a1 stones, a1 stones, two stones can represent nim game like Hackenbush. Okay. Do you have questions? Cut means we take some stones of some pile. Okay. And so on. Okay. We considered combinatorial games, and these games we can classify these games as fair games, and fair games, not fair games, normal games, abnormal games. In fair game, we each player have the same moves, and in normal game, we the last player who cannot make move loses. For example, this will be an unfair game. This was unfair game. and normal, да? Normal game. It's simple. Okay. Okay, we can classify games and any game we can represent as graph. Any game, any combinatorial game, we can represent as graph. So given a graph, an oriented graph, and we have initial vertex s in it. So so our game described like graph and initial vertex. Okay, vertices from which it's impossible to make a move are called terminal. Okay, let's interpret our game as graph on the graph. How many statements? How many statements will was in game of matches? How many vertices do we have? We have. If we consider our graph, if we consider game of matches graph, well, that's obvious. I think we in this game we have for example this edge, this edge, this edge, and so on. No, we have key edges, and we can move in any position. So this is just we have in this case n vertices, in this game we have how many vertices in this game we have? We have initial vertex. Okay, I'm hear you. I don't hear you. So in this game we have n multiplied by m states, and s will be our s will be our initial vertex. Okay, in this we have how many vertices? That's a little bit complex. Let me provide you example. We have example this example in of game, and we have in this game we have edges like this, this. I think you understood. But we have only n to the multiplied by m vertices. In policeman, that's a little bit more vertices. We have this count of coils, and we have, and notice that we have What? And notice that we have two initial vertices in this case. That means we have to multiply by 2, and we and as we have two vertices, not only one, we have to multiply it by multiplied by n and m, because we can make step or step. For example, we have one layer, we have n layers of our game. And we can make like steps like as we have to a little bit confused. So do we need n to multiply by n multiply by m vertices, or n multiply by m and multiply by m vertices? I think it's a question. It's a question of как сказать? We can improve complexity. We can compress our graph, but if in this case, if the most obvious case, we have to do step. We can make step in any of this this vertices, because we have policeman and bandit statements, or statements vertices, no, statements of game.
So the two represent the diagonal move.
What?
The two represent the diagonal move, or what?
This game not fair, and this game is unfair, and we have to split our statements into two groups. Statements, эти состояния. Я забыл как states. We have to split our states into two groups because this game is unfair. And this game have two initial states, but we have only one, and that's why we have to multiply by n to the power n and m. Do you understand me or not? We can compress our graph, but no, with smaller count of vertices, but this is upper bound. This is the obvious upper bound. Okay. Okay. Next, Hackenbush. How many vertices? How many states have Hackenbush? States of graph. Of this graph. The most obvious key the most obvious way to represent this graph, represent the states, is just numerate all the edges like this, and we have for example edges and states of the game will be like will be if we cut now edge, for example, we have one on this place. If we not, we have now, and so on. How many statements? How many states we have in this case? For example, if this state represent this graph like this, we just cut this edge first. Okay, we can make we can cut our edges in any order, but we have we can come to some statement. We have come to some state, and and what? And the count of vertices of states will be like 2 to the power of h plus 1 in this example, because we have 2 to the power of e plus 1 combinations of this sequence. Okay. 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 Do you understand this or not?
So it has E vertices?
We have not the vertices, we have e plus 1. No, okay, we have n plus 1 vertices in this case. E plus 1. Enumerated like this. Because we can, because every state of this game described like, we can describe like we cut some edge or we not, or we didn't cut. For example, if we just cut this and this edge on 3 edge, state will be look like 1 now. Okay, I think you understand now, and so on. That's it. Okay, and this.
But what if we cut an edge and the vertex doesn't isn't dropped?
What if we cut edge and the vertex will not dropped? We have an initial graph. And we know how it looks like. And in this case, for example, if we cut h4, we from our state that describes like this, now and now, vertex now and now, that means no edges cut it. We have an edge to what? 5, 6. We have edge to stamp statement. Null, 1, 1, 1, null, and null. We have different edges. We can, but bar graph represent like can represent like this. Okay. We have no. We can cut any count of edges. Okay, your question is, can we compress our graph, compress our statements, our states? Yes, we can. It can do it, but this is upper bound. You mean if we have?
Yeah, I understand.
If we have now and now and so on. Okay. Why? It's upper bound. It's upper bound. This state is not exist. Okay. The next, we can classify our games like winning game, losing game. If we have some game, and if we have initial vertex, we can classify like this. But notice that if the graph of our graph contains cycle, our game can be tied. What it means? If we consider example like this, n p, yes, n, вот так. This is normal. No, this condition not work isn't work. Yes, don't work to reverse the direction. But we have but we have situations. We have situations. Pn так, вот так, да? Pn this and notice that in this situation, if we have if this is start vertex, we can round кружить by this cycle forever, because okay, first player move to this cycle, this scale, and second player will lose this game because the next is n. The next is the state. The next is the next first player wins, and that's why the second player reverse to this edge, and this game called tie game. If we have cycle, if we have this situation. Notice that if graphs contain cycles, it not necessarily means that this game is tie. Okay, next. Do you understand this? We have this kind of games, and we have to подобрать strategy to define these games, this kind of games. Okay, but we define graphs in which we haven't cycles, cycle graphs. We can apply rule. Apply two rules. We can apply two rules. If we in the first rule we the wins vertices described like this. Okay, if we have some edge and where U belongs to P. This rule and this rule, where for every U, let's do U. What am I doing? No. That's fine. So where U belongs to N. Okay, there are two rules, and the statement our cycle graph can be divided into two non-intersecting sets. This means we can paint our graph like definitely mark our graphs, our vertices. Okay, and why is it true? We take topological. We can prove the statement using topological order. The base of this mathematical induction will be we just mark our leaves as pair, and then mathematical induction step is we just traverse our graph in inverse topological order and in inverse topological order. And notice that we have if we mathematical induction is correct, because notice that if we locate it in some vertex, we know all the marks, because we have already visited it. Okay, and we just apply this step. This step is correct because all vertices that adjacent from some vertices are visited, and we make only one set, and that's it. Okay, I have already told you algorithm how to do it. We just do topological sort of graph and start traversing it from begin of reverse topological order. It means we apply rule. We have for example, for this vertex we haven't positive, I mean pair vertices, that means we have to mark it like pair, and we just make our iterations, and that's it, through reverse topological order, and apply these two rules. Okay, do you have questions? Pool is out. Do you have questions about it? I think someone of you have questions about mathematical induction, or rules, or not. Once again, we prove a statement that we can split our graph into two vertical sets and in pair, and we show how to do it. Okay. Next is strategy. What is strategy? Strategy is it's mapping. It's a mapping that defined on non-thermal vertices, and strategy called winnable is if the first player in a graph game following the strategy, I mean doing this again and again, wins. Apply this again and again on start vertices. Okay, strategies can be different. We have already understood that if we have a cyclic graph, we can find the first player wins or not in some state. Okay, let's let's consider graph with cycles. Let's consider graph in cycles. Sometimes we can't do it. We can't compute our graph, but we for example, what we have this graph. We can apply topological sort on graph with cycles, and for example, if we in this case, if we traverse our graph in reverse topological order, we have that notice that in this vertex we have move to this vertex. It means it vertex is n, and all ends in this vertex. We have all adjacent vertex as marked as n, but in this case, for example, we have to add our rule. If we have suppose all at the beginning of the algorithm, all vertices marked as there, and if we traverse this graph through topological order, the reverse topological order, we get that in this vertex we have эти edges that come we have edges. We haven't any vertices that mark pair, but we have some vertex mark as them. That means we mark this vertex as them, and that's it. Okay, do you have questions about how we supplement our rule, this rule, on acyclic graphs or on graphs with cycles? We input new class there, and we just figure out how to define like game like this. Okay, how to that was interesting, but how to realize, how to implement it, all stuff we discussed. Notice that it's enough to make just one DFS, just launch one DFS, and we can get our graph with cycles, our without cycles. That's not that's not necessary. I think in one path solution. Okay, let's implement it. It's not too hard. One second. Так. Do you see it? No. Okay. Okay. We have our graph. Oi, oi, oi. We have our graph, and in this graph we have. Wait. Second. What happens? I can't see screen. Okay, do you see it? Let me to include libraries. One second. Second. No. I have lux. Okay. Ой-ой-ой. Okay, let me include my library. Uh, how do
I guess there won't be semicolon.
Semicolon? What? Semicolon. I don't understand you. What means semicolon?
The last two dots.
The last two dots. Yeah. Second. No. No. Sorry. I think it's okay. Okay, that's not matter. Don't understand why is it. Why didn't it works?
No, I think it's without точка с объятой.
Точка с запятой. А, блин, ну черт, ну да. Okay. Let's our graph will be represented like this. Unordered map. We need unordered map for where we contain. I think unordered set will be better. Unordered set. Unordered set. Int j. Okay, вот. Remove точка. Remove what? Okay. What? Что такое? Так. It problems. Почему не работает? Ладно, неважно. Я так могу писать. Okay. We have vector int that we in this we mark our так лучше char. We mark our vertices like D, P, and N, we call it just groups. And will be DFS. If we meet that our graph, our adjacent, we haven't any vertices, that means what? That means our vertex where is what? Is pair. We will lose in this vertex in leaves. So and what? Then we just make our DFS and what? And we mark if we meet only if some vertex is what? If some vertex U is what? Is P, P. It means that this vertex, current vertex, is what? Is N. What? Remove, because it's in the same location. I don't. Ладно, давайте let's fix it. Okay, I don't understand why that works. Okay, just do this. Если вас это смущает. Okay, include unordered map. Unordered map is already. What happens? Unordered set, о господи. Unordered set. Unordered set. Okay, unordered set of unordered set. That's true. So, okay. But if we what? If we meet somewhere, if we meet U there, it means groups not U, V is what? No, it's not true. But just 1 second. We can create bool is type. Okay, and do like this. groups. Так. Окей, да. True. Just equal true. And we can break there. There we can break. Then we can return. And there we can just, if our groups, if we have tie game, that means groups where is так, 1 second is there. I think it's true. Okay, else, just else groups where is what is where, if we didn't meet that tie games, that means our game is the first player will lose. Okay, I think we can. Okay, and next is DFS. Ooh. We need to traverse all vertices, all children vertices. And what? And that's and here we just return. I think it's all right. If you see a mistake, can write. G. Так, G. Ну да. What am I doing? Так. Почему это делаю? Ordered map. Ordered map of int and this. And this. GV. We take GV and empty. That's it. And we start from what? We start from for example, we have some function, retrospective analysis, void s, void retrospective analysis, да? Retrospective analysis. Analysis. And it just take some vertex. We have already, suppose we have already как in our graph, and we just launch DFS of this vertex. Do you see any mistakes? I think this is correct. I I did many recursive tasks in the code, and I think it's okay. One second, I think it's okay. Once again, we apply, we split our graphs, our vertices set into 3 groups, P, N, and W. For P, where is it? For N, if there exists edge, from N, just okay, if there is this edge that and U equals to P, we just do this and return, and that's it. Okay. In second, we if we didn't meet any P vertices, it means we just mark our vertex like the mark our and we meet some vertex there. It means we just we mark us like that. We mark that the game is tied, and that's it. I think it's a little bit bug in what place where we okay, let's add some vector char visited. Okay, and just add that visited where is true, because if we meet the situation, it means that that will be bug. What do you? So me and team living. Okay. Okay. No, I already I have already ended. Visited. Where? Let's just return. Okay, that's it. Visited. Boom. Visited. Что я пишу? Visited. Ну, that's it. I think. Okay. Do you have any questions? Thank you. Do you have any questions about implementation?
No, it's all cool.
Okay. So, goodbye.